Hello and welcome to another episode of Risky Business. So last time we wrote the handle trap and we just need to have it use that entry.s file. So I was looking before we started the stream here, and I believe the if we look at the Makefile here, we're including the common Makefile, and it should include the entry.s for us. So I think the work we did last episode is actually going to be enough. So we're going to try to compile it and test it today. So let me just have a refresher here. Excuse me. I believe, it's probably in my history. If we do make software, okay, this is interesting. We get multiple definitions of handle trap. So it's actually pulling in the init.c. I didn't want it to use that, but I do want it to use the entry.s. So what would be the best way to go about that? Here, let me open up another terminal. Okay, now I want this to... Okay, this does include the common.mk, so... So yeah, we see this pulls in init.c. So if we're going to use this at all, we can't really avoid that. We could just not use this, but then we'd have to set other stuff up like the start.s and whatever else this is doing that we would need to do. So in init.c, is there any way without us modifying it to avoid pulling in the trap handler? No. So we might have to modify this. I think one thing we could do is just make a copy of this file and point it to use our copy instead of this one, and get rid of this line. But now that makes me wonder too, if we're including init.c, are we actually using anything from init.c? So I just want to ponder upon this file for a little bit. So we're building our assembly objects, our C objects. We've got our linker script there. These are the C flags we're passing in. So we link the objects. So, I mean, that's pretty straightforward. I guess my question is, like, the stuff that sets things up. Like, something must be calling UART init, for example. Oh, it's the underscore init that's doing that. So if we define no init, that's just saying don't do any of this stuff right here, which is what I am doing. So is there really any reason, you know, if we're going to be pulling this code in anyway, there's not really any reason to not use the init, is there? I mean, it's not like we're doing anything majorly different from this. Oh, so this is... I was wondering about this the other day. I don't know if it was in a book club episode. I think it was the one for the RISC-V reader. Or maybe it was the latest computer organization and design one. I really don't remember. But I was wondering how it handles when you do an instruction that isn't implemented. Like if you don't have the F extension and you do a floating point operation, how does that get emulated in software? Like, where does the implementation live? And I realize now it causes an exception to occur, like in an interrupt kind of exception, that is. So the trap handler would be responsible for doing that. Because what this is doing is it's saying if you have the F extension, set it up to allow you to use them without, you know, trapping on the instruction. Okay. But yeah, what does the use PLL do exactly? Okay. So I think we were doing things a little bit differently than this in our code, but I mean, this is probably fine. I think we're just going to use the init. So what I'm going to do is I'm going to modify the modify the PWM speed test. Although what I'm thinking is if we're using the init, then we can't use our custom handle trap, we'd actually have to go through theirs. Unless we just like copy this file and copy the Makefile and point it to use a custom init.c or whatever. But let's just go ahead and use this one. And then when we do the handle trap, what we're going to do is we're going to define our handle external interrupt, and that's going to do what we're doing here in our actual project. So in the Makefile, what we're going to do is not pass no init. And then in here, we're going to need to change things up a bit. So I feel like we can get rid of these two because we should be able to pull in like a printf implementation or some other printing routine. I don't think we really need these. So we'll look into that in a second. So basically what we're going to do is we have a void handle external interrupt, and it doesn't take any arguments, but all we want it to do is that stuff right there. What was that else attached to? Oh yeah, we can get rid of that. So that's all we want it to do. Now we don't need to set this up anymore. The init will do that for us. And then this stuff we're doing right here, like all of that should be taken care of by the init. Now, the last thing I want to do is change my my put string to like write or printf or whatever they provide. So let me look at what other demos do. So this one's got some printfs. There's also write. I feel like we might as well use printf if it's implemented. Like at some point we're going to be, you know, doing everything ourselves, but this is just a test for, you know, practicing writing some code for the Hi5 and finding out the PWM speed. So I feel fine with just using their stuff. So I'm pretty sure we still want the no built-in printf. But I want to find an example where we're using it. So yeah, like performance counter has no built-in printf, but we see it is using printf. So let's take a look at performance counters. So nothing special in the Makefile. And they just go ahead and use printf, which must be in stdio.h. As you would expect it to be. Now, okay, they don't put the /r at the end of it, so the implementation must be doing that for us. So we're just going to do it like this. So now our demo has simplified a lot. I don't know if we still need all these headers. So let's just comment them out and then try to build it, and then we'll add in headers back one at a time. So we get a bunch of undeclared. So stdio should take care of printf. So let's see, confirm that printf is undeclared, which it is. And if we include stdio, printf should be good. And it looks like it is. So now let's do the PLIC ones. We know we need the PLIC driver, of course. All right. Oh, and we still have one of those in there. Let's change that. I think we need encoding.h. And that built once we put in encoding.h. It does still complain about exit, so we should include stdlib.h for that. And that should be everything. So yeah, now it builds without any warnings. Seems to have built properly. So let's see if we can upload it to the board. Hello, Croeva. Okay, well, it says it successfully uploaded it, despite the errors. So let's give it a reset and see what happens. Well, it terminated before. Okay, there we got a hello world, but it terminates. Yes, we are. We are playing around with our Hi-5 So I managed to get a hello world, but the program terminates after a little while. So, Now, I wonder if that has something to do with it waiting for the interrupt. Like, let's temporarily take out all the fancy stuff. And so this should just print hello world and wait in an infinite loop. So we'll build it, we'll upload it. We will connect to it. So it's terminating before I even get a chance to do the reset on it. It really seems like this this infinite loop isn't working. So what are some other methods of infinite looping? Like we need some volatile something or other in there, so it doesn't optimize it away. Well, this is the one where we got the idea to use the wait for interrupt instruction, but I'm somewhat doubting it right now. I want to try a more straightforward one. So let's check out, I'm sure the demo GPIO did something else. Okay, well they were just bit banging in that one. So again, not exactly what I'm looking for. Well, let me see here. In the init.c, there's the busy loop that we do to wait for the UART to settle. Or am I wrong about that? I thought there was, but maybe not. I mean, maybe it won't optimize it away. So let's see what happens if we build this, upload it. Looks like it's got the same problem. What happens if I put the print in the loop? I'm wondering if it's not uploading correctly. I mean, there are all those errors that we're getting. Let me try we're going to try LED fade demo. But it didn't build. Why didn't it build? I didn't wipe my toolchain again, did I? I did make software clean. I did make software clean, not make clean. I'm pretty sure make software clean is right. I'm confused why this didn't build. What's the... So the work build RISC-V GNU toolchain is empty. So it looks like my toolchain got wiped again. Let me check the forums. I thought make software clean was the proper one to do. How do I see my bookmarks? Oh, software underscore clean. See, I need to be carefuler about my my cleaning when I'm using these make files. So I need to rebuild my toolchain, and this takes a while. Okay, let me see here. Make tools. Let's get that started. So I don't know what we should do while that's building. You know, that's actually not a bad idea. I should probably keep a backup of my toolchain so that when I accidentally wipe it, I can just copy it over instead of having to rebuild it. I will do that after this builds. That's actually a good idea. But one thing we can do is read documentation while it's building, because I'm sure there's plenty of stuff we haven't covered yet. I'm not going to bother with an automated full system backup. This is a risky business after all, so we need some level of risk. But so we could read about the physical memory attributes. The calling convention. We could read about the E31 processor core. The JTAG port. The debug stuff. So this has some stuff we could read as well that would be interesting. I think the thing that would probably be most useful to us to know about would be debug stuff, because when we're working with software, we're kind of just trial and error right now. But, you know, if we can actually debug stuff, that might help. So let's learn about what features are provided for debugging. So there's actually trace and debug hardware provided by Sci5. Okay, wait a minute. This says there's a standard RISC-V debug spec. So where is the standard RISC-V debug spec? Oh yeah, there's GDB support for RISC-V. We just haven't looked into it yet. But yes, that is a thing. Okay, there's debug mode and introduction. Yeah. Implementations may also include a debug mode to support off-chip debugging and/or manufacturing test. Debug mode, or D-mode, can be considered an additional privilege mode. Okay, so it's actually like another privilege mode. That's interesting. with even more access than mmode, the separate debug specification proposal. So there's a separate proposal, describes operations of a RISC-V hardware thread in debug mode. Debug mode reserves a few CSR addresses that are only accessible in demode and may also reserve some portions of the physical memory space on a platform. So we should find the spec for that then. First of all, let me close some tabs we don't need. Okay, so we are looking for specs. There should be a debug one. External debug support. There is O.11 and O.13. Let's just go with the most recent one. 96 pages. Woo. So maybe we won't be looking at this today. This seems like a pretty big thing to get into. But we don't really need... no, I do not have a JTAG cable. Although, if we ever find we need one, I'll get one for the series. But we don't really need hardware support for debugging, I don't think. Like, we don't need to learn about that right now. Like, I feel like we should probably be able to just, like, connect the GDB for RISC-V, like over SSH or something. Or I mean, over screen, like through the communicating through the UART. I'm not exactly how that stuff works, but like if you put it in safe boot mode, they say you can like connect a debugger to it. So I don't know if that requires additional hardware or if you can do it. Okay, yeah, there's make run debug, which will connect with GDB. And apparently you don't even need to put it into safe boot mode. It'll just halt the currently running program. So that's something to try when we have a working toolchain again. So what else would be interesting to look at? Here's a thing on the wait for interrupt instruction. So let's read about that. The wait for interrupt instruction provides a hint to the implementation that the current hardware thread can be stalled until an interrupt might need servicing. Executing the wait for interrupt instruction can also be used to inform the hardware platform that suitable interrupt should preferentially be routed to this hardware thread. Wait for interrupt is available in all of the supported SH and M privilege modes and optionally available in U mode for implementations that support user mode interrupts. If an enabled interrupt is present or later becomes present while the hardware thread is stalled, the interrupt exception will be taken on the following instruction, i.e. execution resumes in the trap handler and MEPC equals PC plus 4. Okay. The following instruction takes the interrupt exception and trap so that a simple return from the trap handler will execute code after the WFI instruction. The wait for interrupt instruction is just a hint, and a legal implementation is to implement WFI as a no-op. If the implementation does not stall the hardware thread on execution of the instruction, then the interrupt will be taken on some instruction in the idle loop containing the WFI. And on a simple return from the handler, the idle loop will resume execution. We have removed the earlier requirement that implementations ignore the RS1 and RD fields. So non-zero values in these fields should now raise illegal instruction exceptions. Okay. The WFI instruction can also be executed when interrupts are disabled. The operation of WFI must be unaffected by the global interrupt bits in M status. That is, the hardware thread must resume if a locally enabled interrupt becomes pending, but should honor the individual interrupt enables. Implementation should avoid resuming the hardware thread if the interrupt is pending but not individually enabled. Wait for interrupt is also required to resume execution for locally enabled interrupts pending at any privilege level, regardless of the global interrupt enable at each privilege level. If the event that causes the hardware thread to resume execution does not cause an interrupt to be taken, execution will resume at PC plus 4, and software must determine what action to take, including looping back to repeat the WFI if there was no actionable event. And they say, by allowing wake up when interrupts are disabled, an alternate entry point to an interrupt handler can be called that does not require saving the current context, as the current context can be saved or discarded before the wait for interrupt is executed. As implementations are free to implement wait for interrupt as a no-op, a software must explicitly check for any relevant pending but disabled interrupts in the code following a wait for interrupt, and should loop back to the WFI if no suitable interrupt was detected. So the MIP, the interrupt pending bits, or registers, can be interrogated to determine the presence of any interrupt in those respective modes. The operation of wait for interrupt is unaffected by the delegation registry settings. WFI is defined so that an implementation can trap into a higher privilege mode either immediately on encountering the WFI or after some interval to initiate a machine mode transition to a lower power state, for example. The same wait for event template might be used for possible future extensions that wait on memory locations changing or message arrival. Alright, so I don't think that really, told us anything too interesting. So let's take a look at the documentation on the calling convention. This chapter describes the C compiler standards for RV32 and RV64 programs, and two calling conventions. The convention for the base ISA plus standard general extensions, and the soft float convention for implementations lacking floating point units. And it says implementations with ISA extensions might require extended calling conventions. All right. So C data types and alignment. We have a table that summarizes the data types natively supported by RISC-V C programs. So we have character, short, int, long, and we see they're using the convention where on 32 bits long is 4 bytes, and on 64 it's 8 bytes. So on 32, if you want to get 8 bytes, you need to use long. Void pointer is 4 bytes on 32 and 8 on 64. That's what you'd expect. Float is 4 on both of them. Double is 8 on both of them. Long double is 16 on both of them. So nothing too surprising there. In both C compilers, the C type int is 32 bits wide. Yeah, that's what we just looked over. And they mentioned the names of the integer models. The 32 one is ILP32. The 64 one is LP64. If you haven't seen those before, there are standard names for the different integer models, and those are 2 of them. So there's actually a variety of different names, and in my NWRMM library, I actually use those. So you can see here, to pick the right type for a U32 in this library, I check for a number of different defines for the model, and then I also have custom ones that you can define if you don't provide any of these. But yeah, those are the like these ones right here, and those ones right there are the standard ones. The standard names that you can look for in your program to figure out what the integer model is. In both of them, long is 64. Yeah, we saw that. Let's see. Okay, so they define the char type to be unsigned character, an unsigned 8-bit integer. That's one thing. Another thing about C is the char type. If you don't specify whether it's signed or unsigned, it can actually be either. It depends on the implementation. So on RISC-V, they define it to be unsigned. Is there anything else interesting in here? It says the compiler and compliant software keep all of the above data types naturally aligned when stored in memory. So you're not supposed to misalign them. All right, next we have the RVG calling convention, and G is the shorthand for your I forget what all it encompasses, but it's shorthand for some standard extensions. The RISC-V calling convention passes arguments in registers when possible, up to 8 integer registers through A0 and A7, and up to 8 floating point registers. And you can see this on the reference cards as well that are provided with computer organization and design, as well as the RISC-V reader. But yeah, floating point registers for the floating point arguments. If the arguments to a function are conceptualized as fields of a C struct, each with pointer alignment, the argument registers are a shadow of the first 8 pointer words of that struct. If argument I is less than 8 is a floating point type, it is passed in a floating point register. Otherwise, it is passed in integer register. Okay. That's interesting. However, floating point arguments that are part of unions are array fields of structures are passed in integer registers. Additionally, floating point arguments to variadic functions, except those that are explicitly named in the parameter list, are passed in integer registers. So sometimes your floating point arguments are going to end up in integer registers, is the takeaway there. And they specify, exactly when that will happen. Arguments smaller than a pointer word are passed in the least significant bits of argument registers. Subpointer word arguments passed on the stack appear in the lower address of a pointer word because RISC-V has a little endian memory system. When primitive arguments twice the size of a pointer word are passed on the stack, they are naturally aligned. When they are passed in the integer registers, they reside in an aligned even-odd register pair, with the even pair holding the least significant bits. Okay. That's interesting. So the way they handle when you're passing something that's gonna, be treated as, split between 2 registers, like if it's a 64-bit type on a 32-bit machine, the way they handle that pairing is they go with the even numbered and unnumbered registers. So the even ones are the low half and the odd ones are the high half of the number. So that's how they handle that. But then I wonder what they do if you have multiple of those. Like, I guess it's the, like the first one and then the closest one to it make up a pair. So then, like, the higher up you go, the next, two would be a pair. If I don't know if I'm explaining that clearly, but I think that's what they're doing there. So they say if you have a function taking an int and a long on 32 bits, and remember long is 8 bytes, so it needs to be split across 2 registers. The int gets passed in A0, and the second one, A2 and A3. But wait, why didn't it use A1? I'm confused again. So, I mean, I get that A2 is being used for the low half of the long. I guess the pairs have to be the odd one following the even number is the high half, apparently. So, like, the pairing has to be A2 and A3 if you're putting the low half in A2. So nothing ends up getting passed in A1 in this case. Arguments more than twice the size of a pointer word are passed by reference. So there's a good rule of thumb, I guess, for you if you're gonna be like writing your functions in C. And sometimes people wonder, like, when should I pass it as a pointer and when should I pass it, directly in? And at least on RISC-V, if you pass by value, but the argument is more than twice the size of a pointer, then it's going to end up internally getting passed as a pointer anyway. So that's something to consider, I guess. The portion of the conceptual struct that is not passed in argument registers is passed on the stack. The stack pointer SP points to the first argument not passed in a register. Values are returned from functions in integer registers A0 and A1. And this is another thing I'm a little bit confused about, that they define multiple return values because C only has a single return. I don't know if they define this for like other languages or what. Like, because I mean, if another language supports multiple return values, I think they would. Oh, you know what? I know why. It's because if you have 32 bits and you're like returning a long, for example, then it needs a register pair. So that's why 2 registers are dedicated, I'm guessing. It's not for like, because I was going to say, if you have like multiple return values, it's not just going to be a pair of registers. You want to be able to support like arbitrary tuples. And yeah, that, a single pair of integer registers or floating point registers wouldn't really do the trick there. So I guess that makes sense. It's just to support when it's larger than the word size. So they give you an integer pair and a floating point pair. Assuming, of course, you have floating points, then you get the floating point pair. It says floating point values are returned in floating point registers only if they are primitives or members of a struct consisting of only one or two floating point values. Other return values that fit into two pointer words are returned in A0 and A1. Larger return values are passed entirely in memory. The caller allocates this memory region and passes a pointer to it as an implicit first parameter to the callee. All right. How much more is this? Okay, there's not too much left, so we're going to finish reading all of this, and then I think we're going to call it a day for Risky Business. When did I start this? 1414. Yeah, so that'll be a good time to stop. So let me see, where were we? Values are returned from, oh yeah, we read this. In the standard RISC-V calling convention, the stack grows downward, and the stack pointer is always kept 16 byte aligned. That's exactly the same as on x86, so nothing too crazy there. In addition to the argument and return value registers, 7 integer registers T0 through T6 and 12 floating point registers FT0 through FT11 are temporary registers that are volatile across calls and must be saved by the caller if later used. 12 integer registers S0 through S11 and 12 floating point registers FS0 through FS11 are preserved across calls and must be saved by the callee if used. Table 20.2 indicates the role of each integer and floating point register in the calling convention. So here we see the table that shows up in the reference cards that I mentioned earlier. So you have x0, which is hardwired to 0, and the API name is just 0. And x1 is RA for return address. x2 is the stack pointer. x3 is GP, the global pointer. x4 is TP, the thread pointer. Then you have x5 through 7, which are T0 through 2. x8 is S0. It can also be called FP for frame pointer. And then x9 is S1, which is another saved register. x10 through 11 are A0 through 1. x12 through 17 are A2 through 7. So the reason they broke those two up in the table are because A0 and 1 are also used for the return values. 18 through 27 are S2 through 11, and then x28 through 31 are the T3 through 6. And then for the floating point registers, you have 0 through 7 being the temporary 0 through 7, 8 through 9 being saved 0 through 1, and then 10 through 11 being A0 through 1, so arguments. F12 through 17 are 2 through 7. And so again, they split it up because 0 and 1 are also used as the return values. 18 through 27 make up the saved registers 2 through 11. And then 28 through 31 make up the temporaries 8 through 11. So that's how all the registers are used. And they also specify who is responsible for saving them if the value needs to be preserved. So let's read about the soft float calling convention. The soft float calling convention is intended for use on RV32 and RV64 implementations that lack floating point hardware. It avoids all use of instructions in the FD and Q standard extensions, and hence the F registers. Integral arguments are passed and returned in the same manner as the RBG convention, and the stack discipline is the same, except that the stack is only kept aligned to xlen divided by 8-byte boundaries. So again, in these documents, xlen is the word size, like if it's a 32-bit processor or a 64-bit one. So, if it's 32, then you're saying it's 32 divided by 8-byte boundaries, so it's a 4-byte alignment requirement in this case. So in the case of the high-five 1, the high-five 1 is RV32, and it does not have floating point. So it would have that requirement. It requires 4-byte alignment of the stack, not 16. As floating point data on the stack will be accessed using integer load and store instructions, there is no incentive to maintain stack alignment in a coarse granularity in the soft float calling convention. The reduced stack alignment saves space in the memory constrained systems that might commonly use soft floating points, so that's why they did that. That makes sense. Floating point arguments are passed and returned in integer registers using the rules for integer arguments of the same size. In RV32, for example, the function double foo that takes an int, a double, a long double, is passed its first argument in A0, its second in A2, and A3 because it's a double, and its third argument by reference via A4. And again, that would be because the long double is it's over twice the size of a pointer. Let's see what else, because that's the long double would be the 128-bit one. And its results returned in A0 and A1. In RV64, the arguments are passed in A0, A1, and the A2, A3 pair, and the result is returned in A0. So for RV64, you're saying the int is passed in A0, the double in A1, because it's 64 bits in this case, so it can hold the entire double. And then the long double, which is 128, goes in the A2, A3 pair. So that makes sense. And of course, we only needed a single register for the return, whereas this one needed the pair, because again, it's a double is the return value. The dynamic rounding mode and accrued exception flags are accessed through the routines provided by the C99 header f-environment, fenv.h. All right. And then we have the RV32E calling convention. RV32E uses a subset of the soft float calling convention, as only 16 integer registers, x0 through x15, are present. There are only 6 argument registers, x10 through x15, 2 saved registers, x8 through x9, and 3 temporary registers, x5 through x7. The stack is kept aligned on a 4-byte boundary. All right, so that ends that. We are still compiling away, but I'm going to end the episode here. So thank you everyone who tuned in today, and thank you everyone who watches on the YouTube archive. You can follow me at HMN_RISCY on Twitter to get updates about the series. And thank you also to everyone who supports me on Patreon. It's greatly appreciated, and it makes the series possible. I don't have anyone new to shout out today. So I will see you guys in the next episode where hopefully we will have a working toolchain again and have it backed up so, this doesn't happen again. But I will see you then. So stay risky, everyone.